Hello, in this lecture we're going to be doing some more additional example problems from chapters 5 and 6. So I have two that I'm going to show you. The first one is going to be chapter 5, so we're going to talk about something that doesn't have any friction. And then the second one, we're going to include friction. So let's get started. First example is going to be a traffic light weighing 122 newtons hangs from a cable tied to two other cables fastened to a support. The upper cables make an angle of 37 degrees and 53 degrees as shown here. So theta 1 is going to be 37 degrees, theta 2 is going to be 53 degrees. Now these upper cables are not as strong as the vertical cable, which is shown right here, and will break if the tension in them exceeds 100 newtons. So does the traffic light remain hanging in this situation, or will one of the cables break? All right, so I want to show you the process and the method for solving all of these force problems. And hopefully you'll start to see a pattern in how everything is set up. The trick really is to set up all of your free body diagrams so that you can convert those into equations. Okay, so let's do a free body diagram of each object here. We want to do a free body diagram of the light, the traffic light, and then also a free body diagram of this joint right in the middle. Okay, so if we do the traffic light, our traffic light, we know that we have tension going up, and we have mg going down, which is the force of gravity. Now in this case, in the problem it says that the object weighs 120 newtons, so this is just going to be 120 newtons. Now if I wanted to do a free body diagram of the joint in the middle, we know that, let's just kind of pencil in our axes here. So if this is our x-axis and this is our y-axis, we know that up and to the right we have T2, which is the tension 2, and then up and to the left we have tension 1, and then pulling down on this joint is going to be tension 3. And these are all vectors. Oops. Okay. Now I also want to draw in the angles. So this angle here is going to be theta 2, and this angle here is theta 1. Because if you look at our drawing over here, if we draw a parallel line, we know that this angle is going to be the same as this angle because of the parallel line theorem. And then this angle is going to be the same as this angle. So I'm just going to, for convenience sake, we want to draw it off of the x-axis in relation to our joint. All right. So now that we have the free body diagrams, we want to start writing out the equations. The equations that we're going to use for all of these problems is just the summation of forces is equal to ma. On the left side is the net force. So you add all the forces up on the left side, and you set that equal to acceleration. Now, in this case, this light isn't moving. We don't want it to move. So the acceleration for all of our equations is just going to be 0. So when the acceleration is 0, nothing's moving. This is a static situation. All right, so basically we're just going to get the summation of forces is equal to 0. All right, so let's do first the traffic light. The traffic light is going to be, so oops, let's say this is for the traffic light. Your summation of force is equal to 0. So on the left side, you want to add all your forces together. So if you look at the free body diagram for just the traffic light, you have anything that's going up is going to be positive, anything that's going down is negative. And this is going to be in the y direction. We can denote that because just like we did in previous chapters, we need to break everything up into x and y components. Well, this traffic light only has y components, so we only need to worry about it in the y direction. All right, so when we add it up, we have tension 3 minus mg is equal to 0. All right, now let's look at the joint in the x direction first. So let's look at x direction. Now, the only parts of these tensions that are in the x direction is just going to be the tension times the cosine of theta, because you can sort of create this triangle here, you know this angle, create this triangle here, you know this angle, so you can find, let me use a different color, you can find what this x component here is. So you have one x component going in this direction, one x component going in that direction. All right, so we'll do, again, the summation of forces, and this is in the x direction, is equal to 0 because it's not accelerating. And we want to go ahead and say that it's going to be t2 cosine theta minus t1 cosine theta, and that's equal to 2. But let's go ahead and fix our thetas here. This is theta 2, this is theta 1. All right. Now, if we wanted to do it in create an equation in the y direction, we have summation of forces in the y is equal to 0. And we see that, let me use a different color actually for the y direction. So the y component is going to be this here, and your t3 down in that direction. Okay, so to get this y component, we're just going to use t1 sine theta. So if we do summation of forces is equal to 0, everything up is going to be positive, everything down is going to be negative. So we have t1 sine theta 1. And then we add t2 sine theta 2. And then we subtract t3, right? Because t3 is going down. All right, well, if we want to simplify this, well, we figured out over here that if we just rearrange this, t3 is equal to mg. So you can go ahead and plug that in. So you have t1 sine theta 1 plus t2 sine theta 2 is equal, minus mg is equal to 0. So if you look, we now have two equations and two unknowns. We don't know what these tensions are, but we do know the thetas. So if you look at, we can call this equation 1, we can call this equation 2. We see that we have t1, t2, and t1 and t2. So we go ahead and take these equations and put them on the next page. We need to figure out how we're going to solve for these variables. All right, so again, our first one was t2 cosine theta 2 minus t1 cosine theta 1 is equal to 0. This was equation 1. And equation 2 was t1 sine theta 1 plus t2 sine theta 2 minus mg. And this is equal to 0. Alright, so what I can do is I can solve the first equation for t2 in terms of t1. Alright, so if I solve this for t2, move this over to the other side, divide by cosine theta 2, you get t1 cosine of theta 1 divided by cosine of theta 2. Now I can go ahead and substitute this value in for t2 in the second equation. So if I take this and I put it into that equation, we get t1 sine theta 1 plus t1 cosine theta 1 over cosine theta 2 times sine of theta 2 minus mg is equal to 0. Right? Now we can just solve for t1. So take this equation here and solve for t1. And when you do the algebra and you rearrange everything, you see that this is just mg divided by sine theta 1 plus cosine theta 1 times the tangent of theta 2. Alright. Well, we know all of these values, so we can go ahead and plug everything in. So this is going to be T1 is equal to 122 newtons, which is our weight. They gave that in the first sentence of the problem. And then we do sine 37.0 degrees plus cosine of 37.0 degrees multiplied by the tangent of 53 degrees. Oops. Okay. And this is just going to give us a T1 of 73.4 newtons. Now, we also need to find T2. So let's go back to an equation that has T2. Probably this equation right here would be a good place to go. So take this and plug that in. So T2 is going to be 73.4 newtons times the cosine of theta 1, which is 37 degrees, divided by the cosine of theta 2, which is 53 degrees. Okay. And this all equals 97.4 newtons. And that's T2. So let's go ahead and look at our tensions. We have this tension here, we have this tension here. The question originally was, does the traffic light remain hanging in the situation, or will one of them break? And if you remember, it said the upper cables are not as strong as the vertical cable and will break if the tension exceeds 100. So we found that the tension is actually below 100, barely in the case of T2, so the tension is not, or the strings are not going to break in this case. So let's go ahead and just do a quick review of what we went over. So we took our picture that was provided to us. We figured out the free body diagrams for each object in the picture. If there's multiple objects, you want to do a free body diagram for each. So we did one of the traffic light by itself, and then we did one of just the joint in the middle that had all the tensions coming together. Then we broke it out and looked at each object individually and figured out an equation, or using F is equal to ma, or the summation of forces is equal to ma. That led us to figuring out what the tensions were. And then once we figured out the tensions, we could compare that to 100 newtons and see if we came in below the 100 newton value. All right, so let's go ahead and move on to the next example. A block of mass m, m2, on a rough horizontal surface is connected to a ball of mass m1. So here we have the block of m2, and there's a ball over here of m1, by a lightweight cord over a lightweight frictionless pulley. A force of magnitude F at an angle of theta with the horizontal is applied to the block, and the block slides to the right. The coefficient of kinetic friction between the block is mu k. The block on the surface is mu k. So determine the magnitude of the acceleration of the two blocks. So what we're really trying to find is this acceleration right here. And they're both going to be accelerating at the same rate because they're part of the system and there's this cord in between them. So the acceleration of both will be the same. All right, so again, we first want to start with drawing free body diagrams of each object. Right, so let's start with M1. All right, so on M1, the only forces acting, we have mg, so it's M1g going down. And we have some tension force going up. For the block, it's a little more complicated. So let's look at them individually. All right, well, we know we have m2g going down for the weight, which means since it's on a surface, there must be some normal force. We don't know where it's going to be, and it's not going to be m2g in this case because there's another force acting. We have this applied force that is up and to the right at some angle theta. And then we're going to have the tension force going back to the left. Now, this tension is going to be the same as this tension. Right? It's the same string, so this tension remains the same all the way through this one string. Right, so in this case, the tension is the same. This is going to be the same as that. Okay, so again, like before, we need to come up with our equations of forces. We always start at the same point. So let's look at summation of forces. We'll go ahead and do the mass of M2 first. All right, so we'll do summation of forces in the x direction. This is of the block. All right, so everything to the right is positive, everything is to the left is negative, and we're only looking in the x direction. All right, so we have this applied force to the right, and to get the x component, we just multiply by cosine theta. So we have F cosine of theta. And then to the left, we just have the tension. So it's going to be minus tension. And that's going to be equal to ma, this acceleration. I can put in the x direction there, but we know the acceleration is going to be the same as this acceleration down here. All right, so this is what we'll call equation 1. All right, now we want to look in the y direction for the block. So equation 2, let's do summation of forces in the y direction. Again, everything up is positive, down is negative, so you have some normal force. And you also have, going up, this component here of the applied force. So that's just going to be F sine theta to get that component. And we want to subtract m2g because that's going down. That is going to be equal to 0 in this case, because the block's on a surface. It's not going to be accelerating up or down. So on the surface, the acceleration is going to be 0. So we'll set that equal to 0. All right, and then the last equation that we want to put together is of the object, this mass 1. All right, so let's use a different color for that. All right, so this is going to be for mass. And we'll call this equation 3. So this is going to be the summation of forces in the y direction because we're using this free body diagram here. Let's say that is equal to ma in the y. But again, this is going to be the same as that. And we can go and sum the forces together. So we have t going up, and we have m1g going down, and that's going to be equal to mass times the acceleration of the object, or of the system, I should say. All right, so now we have 3 equations. At this point, we still need to fill in some of the gaps. For instance, this normal force, we're not really sure about. Oh, also, I forgot one thing earlier. We forgot the frictional force. So let's go back to our free body diagram and include this frictional force in this direction. Right, because if it's accelerating to the right, frictional force is going to be opposite the motion. So we need to add that in up here as well. So we have minus the tension minus the frictional force, oops, and that is equal to mass times acceleration. Okay, all right, so we have this normal force here. Have to figure out what's going on with that, and also this frictional force, we need to plug in some values for that as well. All right, so first thing we want to do is look at equation 2 and solve for this normal force. So when we do that, we see that, switch back to green. All right, if we solve for normal force, we see that the normal force is just going to be m2g minus f sine theta. Okay, so now that we have an equation for the normal force, we can figure out what the frictional force is. So let's do a 4th equation, and we'll call this 4. We can solve for what this frictional force is. Well, frictional force is equal to the coefficient of friction times the normal force. So since we figured out what the normal force is, we can go ahead and plug that in here. So we have m2g minus f sine theta. Okay, and that's all multiplied by mu k. Alright, so the last thing we want to do is substitute this fourth equation and the value for t from equation 3 into equation 1. Alright, so we want to take this, and we want to take what this value of t is and plug this all into equation 1. If we go back to this third equation to find t, you just move m1g to the other side, and you get that. Alright, so on the next page I'm going to combine these all together. Alright, so our resultant, when you add this all together, is just f cosine theta minus mu k times m2g minus f sine theta minus m1 a plus g, just making that simpler, and that's equal to m2 times the acceleration. All right. Now at this point we want to find what the acceleration is. We know all of the values here, the force, the coefficient of friction, theta, g, the masses. Those are all the given variables. So when we solve for acceleration, and we need to be careful because we have an acceleration here and we have an acceleration here, so we need to combine them first, then algebraically rearrange everything, and we end up with the force is equal to, the acceleration is equal to force times cosine theta plus mu k sine theta minus m1 plus mu k m2 times gravity, all divided by m1 plus m2. All right, well, that was certainly an algebraic gauntlet for a question, but these types of things are going to be helpful going forward, being able to manipulate these equations, figure out what you need, how to solve for it, and that kind of thing. All right, that'll be it for this lecture.